Good day, everyone. Welcome to Tagum City National High School Science Web Course on Quarter 2, Force, Motion, and Energy. In this video, we will be applying quantitative analysis of the images formed by mirrors and lenses. Today, we will be applying two equations, the mirror equation and magnification equation, which both are essential in calculating the quantitative characteristics of images formed by both mirrors and lenses. Let us begin with the mirror equation. This equation takes the form of 1 over d sub O plus 1 over d sub I equals 1 over f. D sub O stands for the distance of the object from the center of the mirror. D sub I stands for the distance of the image from the center of the mirror. And F stands for the focal length of the mirror. This mirror equation is very useful whenever we want to determine the type of image formed and its location, which were introduced in the previous video. The next equation is a magnification equation, which takes the form of M equals H sub I over H sub O, which equals to negative D sub I over D sub O. For convenience, M stands for the magnification of the mirror or lens. H sub I stands for the height of the image formed, and H sub O stands for the height of the object. The magnification equation is very useful to determine the size of the image formed by the mirror or lens and its orientation if it is an inverted image or upright image. Now, in every calculations, we will definitely be encountering different signs, such as positive and negative. For our convenience, we will be examining the different sign conventions used in mirror and magnification equations and what they tell us about the image formed. If the height of the image is positive, then the image is upright. If the height of the image is negative, then the image is inverted. If the distance of the image is negative, then it means that the object is located behind the mirror and it is a virtual image. Now, if the distance of the image is positive, then it means that the object is located in front of the mirror and it is a real image. Now, let us try to solve a problem and use the two equations to characterize the image formed by a concave mirror. For this problem, a 1.50 centimeter high object is placed 20.0 centimeters from a concave mirror with radius of curvature 30.0 centimeters. Determine A, the position of the image, and B, its size. In order for us to solve this problem, we need to follow the conventional way of doing or solving mathematical problems. The first of all things to do is to determine what variables are known or given. From the problem, we have three known values, which are H sub O equals 1.50 centimeters, D sub O equals 20.0 centimeters, radius of curvature equals 30.0 centimeters. The second step is to identify the unknown values or those that the problem wants us to find. So from the problem, we have identified three unknowns which include the answer. And these are the focal length F, D sub I, and H sub I. The next step is to solve for the F or the focal length. Of the three unknowns, we must solve first the focal length because this unknown is crucial to solve D sub I using the mirror equation. From the previous video, we know that the focal length of the mirror is 1/2 of the radius of curvature, which takes the form F equals 1 over 2 times C. Substituting the known values, we have 1/2 times 30. Now, if we perform the operations, we get 15.0 centimeters as the focal length. Now, we shall use this value in the mirror equation to calculate the d sub I, or distance of image. Using the mirror equation, we need to isolate the image distance from the rest of the variables. So we have this equation. 1 over d sub I equals 1 over f minus 1 over d sub O. Substituting the variables with known values, we have 1 over 15.0 centimeters minus 1 over 20.0 centimeters. It would be convenient to solve the fraction individually rather than taking the greatest common factor for both fractions. Therefore, 1 over 15.0 centimeters equals 0.0667 centimeters, and 1 over 20.0 centimeters equals 0.05 centimeters. We subtract 0.05 centimeters from 0.0667 to get 0.0167 centimeters. Finally, we swap places of d sub I and 0.0167 centimeters and divide it by 1 to get the final answer, which is 59.9 centimeters, or roughly this is already 60.0 centimeters. This means that the distance of the image from the mirror is 59.9 centimeters. Since the answer takes a positive sign, this means that the image is real image and located in front of the mirror beyond the center of the curvature. Now let us solve for the height of the image h sub I. We use the magnification equation. M equals h sub I equals h over h sub O, which equals to negative d sub I over d sub O. From our previous calculations, we have learned that h sub O, d sub O, and d sub I and their values. Therefore, we only need to substitute those known values in our formula to get h sub I, which is the image height. The final formula that we will use would be h sub I equals negative h sub O. H sub I equals h sub O over h sub I, equals negative h sub O times d sub I over d sub O. Again, substituting the known values, we have negative 1.50 centimeters times 59.9 centimeter over 20.0 centimeter. We cancel similar units and multiply the numerators. The resulting image is larger than the object because 4.49 centimeters is larger than 1.50 centimeter object. Since the sign is negative, this means that the image is inverted. Before we end, I would like to give you some important points to consider when performing calculations. First is to draw a ray diagram even though you are going to make an analytic calculation. This ray diagram serves as a check even if it's not precise. Then apply the mirror equation and the magnification equation. Always follow sign conventions. Sign conventions allow us to determine the characteristics of the image we are calculating. In the next video, we will explore the different ways in which the properties of mirrors and lenses determine their use in optical instruments. See you there.